Thank you very much, Andre, for this kind introduction. And thank you to you and Daniel for giving me the opportunity to present some of my recent work related to ISS in this seminar series. The outline of my talk would be this one. I will start with an overview of some results on this topic, ISS on switch systems, some of the earlier results. Then I will basically discuss the limitations of those results. Limitations is probably a harsh word. Basically motivate in which directions I am generalizing them, and then some recent work about computing new dwell time conditions for ISS. And finally, we will see an application of these concepts in the context of analyzing interconnections, which appear basically in sample data control of such systems. And I will then conclude, I will leave some room for concluding remarks at the end. Okay, as you can see in the outline, there are three main sections after the overview that I will cover, which appear over here. And for each of these sections, there's a primary reference. The first one has not published yet, but we have put it online. And then there's the second one, which has appeared in, which is published online in MTSS. And then there's, for the last section concerning interconnection and sample data control, there's a paper in Automatica. Right, and so let me start then with some basic notions. So we are looking at time-dependent switch systems, which basically means that we have a family of locally Lipschitz vector fields, which are indexed over some discrete set, which I denote by calligraphic P. There is a switching signal in our system description, which determines the active vector field at any given time instant. This switching signal is therefore a mapping from the set of positive reals to this index set P. We assume it to be piecewise constant, right, continuous, and there is no accumulation of switching instants over a finite interval. So just some classical assumptions which allows us to deduce that the solutions are well defined, right? And we will use this notation capital sigma to denote the set of switching signals, right? Then the assumption on the input is that it is locally essentially bounded, right? Nothing more. And under these assumptions, we can show that so I will not go into any complicated stuff related to existence of solutions. We can show that for this kind of a setup, the state is going to be an absolutely continuous function with some domain over which the solution is defined, right? And I am not looking at the state resets in this talk for the sake of simplicity. One can introduce these state resets, but the kind of ideas that I want to present I would think it would be better not to go into such details. But the work, the results that we have actually do deal with state resets. So, okay. So this is the basic setup. We have this system class, and for this system class, we consider generalized stability notions for ISS, which is defined as follows: that we say that the system is uniformly input to state stable over the over a set of switching signals sigma. If for each, if we can associate a class KL function beta and a class K infinity function gamma, such that this estimate holds for every switching signal and for every initial condition and every input, right? So compared to the conventional notion, what we impose here is uniformity with respect to the set of switching signals, okay? And similarly, you can define the notion of integral ISS, and it is again the same idea. We have a classical estimate where the sup norm is replaced by a kind of an integral norm, L1 norm, and we require that such an estimate holds for the entire set over the entire set sigma that we are looking at. And when you have resets in the system, the notion of integral ISS gets modified slightly. You have an additional term due to the values of the which basically takes into account the values of the input at impulse times, right? But let's say I'm not going into these details. Okay, so once I have defined the switch systems and the related stability notions, the third ingredient in the title is the notion of dwell time. Notion of dwell time basically is rather classical one in the literature on switch system. It basically says, it basically puts a bound on how fast the switches can occur within our class of switching signals that we are looking at. So it is formally quantified by this kind of an inequality, which says that over an interval on average over an interval of length tau a, we can have only one switch modulo some integer n0, which captures somehow the shuttering bound. So when n0 is equal to 1, we have the conventional notion of the dwell time, which basically says that over an interval of tau d, we can have at most one switch, and average dwell time just allows some additional rapid switches, but on average, it has to obey a distance of tau a time units between consecutive switches. Okay, so this notion was, the notion of dwell time was first, to the best of my knowledge, formulated by Professor Morse in a paper in Transactions that appeared in 1996. Then he was looking at a supervisory control problem. That's where this notion first appeared. Then Heshpina and Morse generalized this dwell time notion to average dwell time notions while studying asymptotic stability of switch systems. And besides switch systems, these notions also appear in analyzing the stability of impulsive systems. So you don't have the vector fields which are switching, the vector fields remain the same, but there are jump maps from time to time. And these notions have been useful in those contexts as well. Okay, so let me present one of the first results about ISS and dwell time, which was co-authored by Professor Liberzon in 2007 in an Automatica paper. So it basically, this is, I would say, the simplest setting in which we have ISS for the switch system under dwell time notion. It basically requires two hypotheses on the system data. The first one is that each subsystem is ISS, and the way we write down this assumption is by imposing these inequalities over here, right? We assume that for each subsystem there is a Lyapunov function v sub t, which satisfies these sandwich growth conditions, where alpha p are actually class K infinity functions. And moreover, the derivative along the vector field of this function v satisfies this inequality. So this is an exponential decay of the Lyapunov function v sub p, okay? Right. And then there is an additional condition which we call compatibility condition somehow between different Lyapunov functions, which says that the value of each Lyapunov function must be bounded by this inequality. V sub q is the Lyapunov function associated to another subsystem. So this should hold for each x in Rn and for each p and for each pair of modes that we are looking at, right? So in the first hypothesis, the decay is characterized by this scalar lambda, and in the second hypothesis, the growth at switching times between while jumping from one Lyapunov function to another is captured by this constant mu. And this result is rather nice, that the system is going to be uniformly in ISS over this intervals over this set sigma tau a, which is the set of switching signals which respect the average dwell time tau a, and tau a satisfies this lower bound. right? So in the numerator, you have the growth due to this scalar mu. And in the denominator, you have this decay rate lambda. So larger the decay rate, the smaller the bound, and vice versa. Okay, so this is a nice lower bound, but in deriving this lower bound, we impose some assumptions. The first one is that, and the restrictive assumption is that we require some kind of a compatibility. Okay. And basically the result just says that if each subsystem is ISS with exponentially decaying Lyapunov function, and these Lyapunov functions are compatible, then we have a finite lower bound on the average dwell time, which guarantees ISS for the switch system. Now, I would say that requiring each subsystem to be ISS seems rather natural, but having this pair of assumptions that you must have an exponential decay plus this compatibility, which basically says linear growth, is it restrictive or not, right? And if it's so, to what extent it is restrictive? So I was recently looking at these kind of questions, and these are this is the direction in which we will generalize this result in the remainder of this talk, or at least in the next two actions. And it turns out that compatibility is very restrictive, right? If you impose ISS, you can always modify the Lyapunov functions to get the exponential decay, but then this compatibility condition would not hold, right? And then if it is restrictive, then if you don't have this condition, what are the analogs of this aforementioned result that one can develop, right? By dropping this condition. So this is, these are the couple of questions actually that we will address now. And so this is one set of generalization that I am going to address, but in the literature, you see, based on this work, we see a lot more work that has been done, which combines the notion of dwell times, rather in the setting of impulsive systems or the switch systems, right? So here I have listed a few references, but I would say this is not exhaustive, but it is somehow closer to the approaches or the framework that we are adopting here. Okay. Right. So the first thing is I want to be more precise about what is the limitation of these conditions that we impose in the classical result, right? And I will formulate my question in the form of this rather simpler implication. So remember that I'm looking at how restrictive it is to assume that each subsystem has an exponentially decaying Lyapunov function plus a compatibility condition, right? So to answer this, let us look at a simpler setup that we have an autonomous switch system, and for each subsystem, we assume that the origin is globally asymptotically stable, right? And we want to ask ourselves whether this is enough to ensure that there exists a dwell time such that the switch system is going to be uniformly globally asymptotically stable over the set of switching signals with that particular value, with dwell time. So this can be arbitrarily large. So I'm just assuming the existence of a dwell time question under this simpler assumption, right? So note that having such an assumption, which I have on the left-hand side, having such a condition that I have on the left side, implies that there exists a Lyapunov function for each subsystem, right? And we can always choose it to be an exponentially decaying Lyapunov function. So that assumption is somehow hidden here. What is not I'm supplying is a compatibility between different Lyapunov functions, right? And if I want to find an answer to this question, so what comes out is that the answer is no, right? And we did not find any paper where it was cleanly formulated, the answer to this question. So we looked into it a little bit. Although some of the recent work in the group of Professor Liberson has provided some examples, I would not say we are the first ones to make such observations. But in this setting, we were trying to look for a cleaner answer, and the implication turns out to be no. And the way we arrived at this answer is by looking at the following kind of example. So we took two vector fields, and these vector fields are of this form. So there is this linear part in it, and then it is multiplied by some scalar, which is the norm of this linear part to the power k minus 1, right? And these AP matrices are some special Hurwitz matrices, which are taken from an example in this book. And I will show you why we choose them in a particular manner as in this book in a few minutes. But already you can see that if I take k equals to 1, then this corresponds to the linear case. And if I take k is greater than 1, then this is a superlinear case. So the decay is very slow near the origin. And if I take k less than 1, then the decay is very slow far from the origin. So these are the regions where the problem somehow would occur, right? Corresponding to different values of k. And this is what we see through this example. Right, so just to give you a glimpse of what goes wrong if I pick k greater than 2, in particular, if I pick k equal to 2, I get this kind of a system. And the way we look at this undesired behavior is as follows. So I pick some initial condition, which is denoted by this black dot in the figure. And I try to find times t1 and t2, so that if I travel for t1 time units along the first vector field and for t2 time units along the second vector field, I arrive back at this initial condition, right? So for this example, we could find such times. Now, what happens is that if I take the initial condition closer and closer, if I scale this initial condition to make it smaller and smaller and converge it to the origin. So let's say the scaling factor is lambda, the times get scaled by a factor of 1 over lambda squared, right? So the closer I get to the origin, I can form these kind of orbits, but the time it takes me to make these orbits gets arbitrarily large, right? So in other words, no matter how large a dwell time I pick, I can always find an initial condition close to the origin, which would not actually be converging to the origin, and it will be stuck in this kind of a periodic orbit, okay? And so this means that this is a system for which no matter how large which has each of its vector fields asymptotically stable, no matter how large a dwell time you pick, you would the state would not converge to the origin. Okay, you can find such a switching signal with arbitrarily large dwell time, right? So near the origin, we don't get convergence when k is greater than 2, and I was saying because the decay, the rate at which the solutions decay to the origin gets very small, and this causes a problem. And you observe a similar phenomena, but away from the origin when k is less than 1. In particular, no matter how large a dwell time you pick, you will always be able to find initial condition large enough away from the origin such that the solution actually diverges to the infinity, right? And the phenomena that I observed in these two examples can actually be generalized for a class of homogeneous systems where each vector field is homogeneous, okay? And what we do, and to show what is the negative result that we obtain, just bear with me. I need to introduce one last piece of notation, which is this vector field G sub P associated with the vector field F sub P. So F sub P is the system dynamics, which is homogeneous of degree K. Now, associated to this vector field, I introduce another vector field, which is G sub P, and this particular vector field is actually homogeneous of degree 1. Okay, so well, this is a transformation, and the reason for introducing this transformation is that we can relate the solutions of the original system via the system through some kind of a scaling. Okay. And if you look at our example that I just mentioned with this FP as the vector field, if you try to find this GP, this would be simply this matrix A sub PX, right? And like I said, this is exactly the linear system that was analyzed in the work by Professor Liberzon. And what happens is that for this system, we can find a switching signal with a positive dwell time, such that the solutions diverge to infinity. And this is the observation that was important for us. And what we see now is the following statement that if you consider these switch system where these vector fields are homogeneous of degree k, and you associate with them this auxiliary switch systems obtained from the G vector fields. So G are basically a nonlinear transformation of the F vector fields. And you can find a switching signal for this switch system, or for this auxiliary switch system, such that the solutions diverge to infinity. Then what you can conclude is the following, that the case k greater than 1, no matter how large a dwell time you pick, the original system will not have an Lyapunov stable origin. And if k is less than 1, no matter how large a dwell time you pick, there will always exist initial condition and switching signals of that dwell time such that the resulting solution diverges to infinity, right? So we have been able to quantify or give some qualitative answer to the fact that even if you have globally asymptotically stable origin for each subsystem, having sufficiently large dwell time is not enough to guarantee asymptotic stability of the switch system, right? So it's not just that you can come up with a negative answer, there is also some positive answers you can come up with, which basically say that, well, even though in the first case, k greater than 1, you will not have the origin which is Lyapunov stable, but you will have ultimate boundedness. So you will converge to some ball around the origin. And in the case k less than 1, even though the solutions far from the origin diverge to infinity, but you still have local asymptotic stability, right? So these are the kind of results that one can formulate, right? So this shows that if you just have asymptotic stability of the vector fields, this is the best one can hope in the generic case, okay? With dual time type conditions, okay? So now I will move to the second part of my talk. So from negative results, I will move more to the positive results when it is possible to get asymptotic stability. And actually more consistent with the theme of this series is the question related to input to state stability. So let me just recall this implication. So in the previous section of my talk, I had this, I was looking at autonomous systems. So I had formulated a question in terms of zero gas. When we have an input, we will obviously make this change in our implication. And I claim that we have already shown that this implication does not hold, right? Because zero gas is a particular case of ISS, and we have already seen basically the insight into the case that this kind of an implication would not hold in general, right? So we need to strengthen the left-hand side to be able to find lower bounds on dwell time, average dwell time, for such that there should have been a D here, sorry. Such that our switch system is going to be uniformly ISS over this set, right? And in the earlier work, as I mentioned, they added some kind of a compatibility condition, but this is somehow very restrictive. So we want to generalize this kind of work, and so we will do so by introducing ISS Lyapunov functions for each of these subsystems. And what we will do in these our work is that we will not impose exponential decay or linear growth at switching times. We would work with generic functions, generic nonlinear functions, and we call them nonlinear supply functions, hence the name. Which allow us to compute more generic ADT bounds, which guarantee uniform ISS over that class of switching signal, over the corresponding class of switching signals. And as one can then do generalizations in several ways. You can also allow for some subsystems to be non-ISS and things like that, as long as their activation period is small compared to the dwell times that you're computing. But this is not the focus right now. The focus is that we are generalizing the earlier work by imposing nonlinear supply functions in our dissipation inequalities associated to the Lyapunov functions of individual modes, right? So let's do that. So right now I will make this kind of an assumption for each of my subsystem, that I associate a Lyapunov function V sub p to each subsystem, and it satisfies these classical bounds. And then there is this dissipation inequality where instead of exponential decay, we just assume that there is some class K infinity function over here. And at the jump times, we assume that there exists a class K infinity function which captures the growth due to the change in the Lyapunov function from one subsystem to another. Okay, so earlier we had lambda here and a mu constant here, but now we have alpha and chi, and we want to ask ourselves how do the dual time bounds change because of this modification. One remark I want to make here, that one can consider the case of integral ISS also with a similar methodology, where instead of taking alpha in class K infinity, one can take alpha to be a positive definite function, and the remainder, and there's not a lot that changes in the sequel actually, and one can claim integral ISS as well. So in this talk, I mostly fixed to the ISS, but whenever I'm referring to the integral version, it means that this function alpha is actually positive definite and not class K infinity. Okay, so let us see how this notion generalizes. So what we do is that once we have these alpha functions associated to the dissipation inequalities of our individual Lyapunov functions, we construct this auxiliary function psi. C can be some constant, so you can say that this function is parameterized by C, but it can be anything. And the key assumptions that we now assume, or you can say, is the following. We have an integral from S to chi of S of this function psi, which is defined here, and we assume this to be finite. When we were in the linear case, this psi was a linear function. So when you take alpha to be the linear function, then the psi would just be equal to alpha. And this chi was a linear function. So you could solve this integral expression explicitly, and you get the same lower bound actually as you had before, right? So in the linear case, this constant will always be finite. But in the nonlinear case, this is not really the case, and it depends on how your decay function alpha is related to the growth function chi for this entity to be finite, right? This is the additional condition, which if we do this generalization that I mentioned on the previous slide of introducing generic nonlinear functions and the dissipation inequalities, then this is the assumptions, that the additional assumption that we need for the existence for guaranteeing ISS, and as I will show on the next slide. This finiteness also essentially captures a trade-off between the continuous flow and the growth due to the discrete dynamics, right? So, so to formulate the result, we have to basically adopt this kind of a framework of hybrid systems, where we describe the dynamics during flows, and then the jump maps. Basically, the interest for this talk of showing this slide was that we could capture the ADT notion by introducing this kind of a timer. This is already explained in this book. And so the solutions actually have a solution of this hybrid system respect the average dwell time constraint, right? Because of the way we define this timer. And the reason for introducing a timer was that I could explain the construction of our Lyapunov function in this, which appears in this result. So we assume basically that these certain dissipation inequalities hold associated to each Lyapunov function, and some growth condition holds at jump times. And that constant size star, which was defined in terms of a supremum of an integral, is finite. Then the switch system is uniformly ISS or integral ISS, depending on what is the assumption on decay rate function, for each average dwell time, which is greater than its size star. And moreover, one can associate a hybrid Lyapunov function, hybrid ISS Lyapunov function to our system, which is in this form. And the function phi is defined as in this way. It takes a bit of time to arrive to connect all the dots on how we were able to connect them to be able to derive this expression. But you have this function phi defined like this, and in the Lyapunov function we have phi of v sub p multiplied by some exponential growth exponential function, and then this phi inverse, right? Once you have this kind of a candidate, what we basically do is we compute its derivative along the flows of the system, and we compute its growth along the jumps, and invoke some results on ISS input to state stability of hybrid systems to show that all the conditions that are required are satisfied by this candidate Lyapunov function, and this allows us to guarantee that the system is our switch system, original switch system is ISS with this value of average dwell time, with this lower bound on average dwell time, right? So this is a particularly simpler setup of what we can deduce. As I mentioned, that we could allow for some unstable modes in our system as well. The way we would capture the presence of unstable modes is via this kind of an inequality. So the unstable system have their own function v sub p associated with them, and its derivative along the dynamics of that system has some positive definite function alpha u, and some it could be positive definite function, I did not write a class, or positive definite function gamma. And then, so because we have some unstable dynamics in the system, what we want to do is limit the activation times for our unstable modes compared to the stable modes. And this is captured via this kind of an inequality. So if you take eta equal to 0, eta is somehow the fraction of the activation times over an interval that we associate with our unstable mode. So if you take eta to be 0, you recover the previous result, which is when all submodes are ISS. But due to the presence of these unstable dynamics, you have to make sure their activation time eta is small enough to be able to satisfy this inequality. And as long as this activation time is small enough, then the resulting system would be input to state stable. Here I am introducing a kappa. Kappa is somehow the supremum that you associate with this with the introduction of this alpha u dynamics and the psi dynamics that were associated to your stable. So this is somehow a ratio of unstable dynamics over stable dynamics, which and the maximum over that, which is captured by this constant kappa here. Okay, so this is a generalization that one can achieve, and somehow the corresponding result would have a slightly different Lyapunov function. Some details change, and you have to introduce an additional timer in the hybrid systems dynamics for capturing the unstable dynamics. So some details change, but on a higher level, we have the and we are following the same principle, right? Finding a Lyapunov function and associating it to certain hybrid dynamics. And as I said, one can also allow for reset maps at switching times, which of this form. And this introduces some additional function or different function possibly due to of state and due to the input D at the jump times. Essentially, this does not bring any change into the formulas that we try, but some details change. Because we in our paper we have quite a few examples where the classical setup with the classical setup we could not be applied, but the generalized results could be applied. And the particular example of interest that I found interesting is the integralizers of switched bilinear systems could be deduced from there. And this is the setup where alpha is actually positive definite, and this is really the case where we see a considerable difference compared to our earlier results. And then there are some examples where you see that the stability can only be achieved by at sometimes slow. On the large scale there should be a slow switching, but some modes cannot be activated for too long, even if all the subsystems are ISS. So there are some interesting examples, and credit goes to my co-authors for that. So if you are interested in what is the utility of these results, we see it in these examples. Okay, so this is so this set of results captures basically a generalization of the classical ADT condition, and now I want to study the application of this last method in analyzing interconnections, and the motivation for the interconnections that I've been looking at is arising from the problems related to sample data control. So let me quickly state somehow a fact that would probably be easier for you to arrive at based on what I presented in the last section. It is that let me consider a cascade interconnection of X dynamics with E dynamics. Both of them are switching, okay? But I take the switching signal to be the same for both of them, right? So X is driven by E and E is driven by D. So we have some modes, right? The number of modes is actually the number of modes is the same for both of these subsystems, the E and the X system. And there's a Lyapunov function being associated, which characterizes the ISS property for each of these blocks, right? Each of these subsystems in both the blocks. So we denote for the ones for the E dynamics by VOP and one for the X dynamic by V sub P. And the ISS notion can be captured via these dissipation inequalities, right? Now, since each of them is ISS with respect to the input they are getting, what we can show is that each subsystem is actually a cascade interconnection of two. And if we can find a Lyapunov function for the cascade interconnection, then we basically just have a switch system where I can associate a Lyapunov function with each of these modes, and I'm just switching between the two, right? Switching between over this finite family of cascade interconnections, right? And this one can do, so when we were studying this problem, we took a look at construction, which is particularly inspired from this paper We wrote it explicitly in a CDC paper, but yeah, so this is the kind of construction that we were looking at, where LP is some kind of an operator. It is somehow involves an integral expression and the corresponding gain functions that you see over here. Okay, but one can write down such an operator, such a function, and associate the kind of inequalities that we need to apply our previous result, right? And also you can associate the chi function when you switch from one function to another. But the point is that you can analyze cascades in this simpler setting, where the switching signal is the same for both of them via our framework, so you can associate them. And why am I looking at the cascades? Well, my motivation was to look at the feedback stabilization problem of nonlinear systems, which can be solved by breaking this loop into a cascade interconnection, right? And this is somehow we see in the literature, and for certain control design methods, we can basically design an observer and make the controller a function of the observed state, and such settings, when they are applicable, can be written down as cascades. Also, what we need additionally here is the robustness with respect to the output measurements in the output. So overall, when you have such a design problem, we can break it down into a cascade form, which is depicted at the bottom of the screen, right? Where E dynamics are basically representing the state estimation error, which comes from designing an observer. And if they are ISS with respect to the measurement errors, we often arrive at an analysis of this form. Okay. So this is the motivation for looking at the cascades for us. And where do we come up with this is that we were basically looking at the problem of designing feedback stabilization. We are looking at the feedback stabilization of a switch system subject to sample measurements, right? Sample at the output and sample at the input as well. The way we do it is we design some kind of a filters over here, which will determine the sampling instance. So there is an additional algorithm involved here. But for the sake of this talk and to make connections with what I presented earlier, what I want to show is that this loop that we have over here can be can be broken into a cascade interconnection, and these eta O dynamics and eta C dynamics, which determine the sampling instance, are actually can be analyzed slightly differently, but one can use the principles or the Lyapunov functions that I designed earlier to analyze such kind of systems. I have some, so basically what I do is I define these filtering algorithms actually based on the gain functions that are associated to the cascade interconnections of the nominal system. And I can define some kind of a sampling strategy as well, which is somehow, which is more commonly known in the literature by event-based sampling, which says that whenever certain error gets large compared to a threshold that is set based on the dynamics of this filter, then I send a new sample. So there is some additional hybridynamics due to the filter being involved here. But overall, we have this kind of a picture that if the closed loop system under appropriate assumption on Lyapunov function associated with the nominal system has nice properties, right? So if the observer error dynamics of the observer has ISS properties, and full state feedback controller has some kind of ISS properties, then these are the kind of assumptions that you associate. And based on the gain functions that we have in those inequalities, if we design the sampling algorithms appropriately, the filters that I showed you, then we can have asymptotic stability of the closed loop system, provided the average dwell time satisfies this kind of a bound. And once again, we see the similar bound that I showed you earlier, right? And the idea of analysis is somehow simpler, is similar, where you see that I try to pick a Lyapunov function for the overall system, for the closed loop system. And when there were no eta dynamics, these are the dynamics for which are due to the filter, which are used for designing sampling instance. My Lyapunov function is exactly the same that I showed you earlier. Well, almost exactly the same. And due to these additional dynamics, I can just add them up over here. The individual Lyapunov functions are the one that I showed you were due to the cascade nature of the problem. The assumptions I make allow me to break the loop into a cascade. And this comes up over here. And yeah, so you can associate this big Lyapunov function, and under a similar dwell time constraint on your switching signals, you can do some kind of analysis of the overall system to deduce asymptotic stability. It's slightly more complicated because of these additional dynamics, but just to the big message here is that one can take the analysis that I showed you in the earlier part of the dynamics to such classes of design problems, right? And what I really found helpful was the fact that I could associate a closed loop Lyapunov function with the overall system. So that was really helpful in taking this a step, I think. Then we have, I have an example to illustrate the strategy and this sampling behavior that I just mentioned. So we have some linear dynamics and then some nonlinear dynamics. With each of them, we can associate quadratic Lyapunov functions, and we can associate these dissipation inequalities. And once you have that, you follow the procedure and you get this kind of a profile, actually. So these are some of the states that are getting reset due to oversampling. So you fix a profile based on the gain functions. These are the red profiles. And this is showing that if this is, you're monitoring the error between last sample output and the current value of the output. And when it reaches a certain threshold, you reset and you wait until you hit the threshold again. And so this is the kind of behavior that you get from designing the dynamic filters that I showed you, right? Yeah. So this is all the material that I wanted to cover. So let me summarize it. So what I started from at the beginning of my talk were this classical result, which guarantee ISS for switch systems under some lower bound on average dwell time. And the statement of such results requires exponentially decaying compatible Lyapunov functions in the formulation. We saw that this is somehow restrictive. We analyzed the restriction of such results by saying that if each subsystem is gas, typically we do not have the gas property for the overall switch system, even for arbitrarily large average dwell time. Same holds for ISS. And then we studied sufficient conditions, a different set of conditions to guarantee ISS. And in the process, we computed a more generic lower bound on the average dwell time. And this condition boils down to the finiteness of this integral. And particularly pleasing aspect for me was to see that in the linear, when we were having linear constants in the exponentially decaying compatible Lyapunov function, you saw this nice trade-off between growth at discrete times and the decay during the flows. And this condition also captures that, but in a slightly more complex fashion. The psi is due to the growth, the decay associated to the Lyapunov functions during flows, and chi is somehow the growth associated to the Lyapunov functions at these switching times, right? And in the process, we constructed Lyapunov functions, hybrid Lyapunov functions for the analysis. And the construction of such functions was particularly useful in studying some design problems when we are looking at sample data measurements. The controller only has access to sample data measurements. So this was the overall summary of my talk. I'll be happy to take any questions you may have, but let me first thank you for being here and thank you for your attention. And Happy New Year.